Hi everybody. In this video we're going to practice finding the direction of the magnetic field produced by a very long current carrying wire. Alright, so just to recap, from the Biot-Savart law, which is this expression where mu naught is a natural constant with this value in these units, Teslas times meters divided by amperes. From the Biot-Savart law we can derive the magnitude and direction of the magnetic field produced by a long current carrying wire. First, how long is the wire? Technically, for this expression to be exact, it would be an infinitely long current carrying wire. But this expression is a very good approximation as long as r perpendicular, the distance from the wire to where you want to know the magnetic field, is short compared to the length of the wire. All right, so this is the magnitude expression. What we're going to do is focus on the direction. The direction part for finding the magnetic field due to a very long current carrying wire. The direction part is a derived right-hand rule. And that derived right-hand rule has its origin in a right-hand rule coming from this cross product here in the Biot-Savart law. So I go over that in another video. Here we're just going to practice using the derived right-hand rule for this specific configuration, a long current carrying wire. So to summarize that derived right-hand rule, what you do, let's imagine this is the long current carrying wire and the current is, say, in this direction. Stick the thumb of your right hand in the direction of the current, your fingers wrap in the direction of the magnetic field. Now that seems like a very rough guide, but remember, the magnetic field produced by a long current carrying wire basically makes circles around the wire. The whole purpose of the right-hand rule is to figure out, are the circles of the magnetic field vector arrows going this way or are they going this way? So if I stick my thumb in the direction of the current, my fingers wrap around, I know that the arrows go this way. So above the wire, the magnetic field will be coming out of the board. In front of the wire, the magnetic field will be down. Below the wire, the magnetic field will be in. And behind the wire, the magnetic field will be up. Okay, so what you practice using that derived right-hand rule for the direction of the magnetic field due to a long current carrying wire for each of these examples. Let me just explain what each of the examples are. Here I've got a long current carrying wire with the current going this way. So you need to find the direction of the magnetic field that wire produces here and here. Here I've got a current going to the right. Find the direction of the magnetic field that current produces here and here. Here I've got a wire basically oriented this way, and the current is coming out. The little dot represents outward coming current. Find the direction of the magnetic field that current produces at locations here, here, and here. Likewise here, another wire oriented this way, but this time the current's going in. Find the direction of the magnetic field that current produces there and there. All right, so take a couple minutes, pause the video, work all those things out, and then I'll go over the answers. Okay, so hopefully you've paused the video. We're back. I'm going to go over the answers. I'm just going to use this derived right-hand rule. So for the first current going down, I stick my thumb of my right hand in the direction of the current. My fingers wrap in the direction of the magnetic field. So here, the magnetic field is into the board, and over here, the magnetic field is out. In and out. And those directions are the directions of the magnetic field produced by this current carrying wire. All right, a current going to the right. Stick my thumb in the direction of the current. Above the wire, my fingers are going out. And below the wire, my fingers are going in. So I've got out and in, respectively, for the directions of the magnetic field above and below the wire. And just if we wanted to be more complete, if I wanted to know a location out here, the magnetic field would be down, for example. Okay, now let's look at these. I want to know the direction of the magnetic field produced by this long current carrying wire with the currents coming out of the board. So I stick my thumb of my right hand again, thumb of my right hand in the direction of the current. My fingers will wrap around. So I know the magnetic fields make circles around the wire this way. Now what does it mean to be on a circle? It means to be perpendicular to a radius. So if I want to know the direction of the magnetic field at this location, I draw a little radius. If I wanted to label that, that would be r perpendicular in this formula if I were trying to find the magnitude of the magnetic field at this location. All right, so all the right-hand rule, this derived right-hand rule for the direction of the magnetic field produced by a long current carrying wire, all that's doing is trying to tell me, is the magnetic field direction that way or that way? Because that's all this versus that does. So the current's coming out, fingers wrap this way, magnetic field must be that way. And that's perpendicular to the radius. All right, I can do the same thing here. Draw myself a little r perpendicular. Draw another r perpendicular right there. All right, so fingers wrap this way. Magnetic field must be this direction, perpendicular to that r perpendicular, and this direction. That's all consistent. So all the right-hand rule is telling me whether these arrows go this way versus that way, or this way versus that way, or this way versus that way. All right, so we look at this one. I could do the same thing, except now the current's in, so I stick my thumb in the direction of the current, my fingers wrap around. All right, I'll draw my little r perpendiculars. And this time, thumb in of my right hand, fingers wrap around, so I know my magnetic field's got to be this way and this way. All right, there you go. So one key takeaway from all of this is the right-hand rule. Don't expect it to do too much for you. Like, you stick your thumb in the direction of the current, and these fingers are kind of in a floppy direction, but all they're trying to do is tell you whether the circles go, if here's your current, are the circles going this way or are the circles going that way? That's all the fingers need to do. If you need a precise direction, when you've got your current direction, you can draw yourself a little r perpendicular from the current to the point where you're interested in and figure out. All the right-hand rule is telling you is whether the magnetic field goes that way or that way, for example. All right, so I hope that helps, and we'll see you next time.